Okay, I'd like to talk a little bit about the kinetic energy of a rigid body. Say I have this body here represented in blue, moving through xy space. We have a velocity at p and a velocity at q, so this body is general plane motion here. Well, we can define a kinetic energy, T equals 1/2 mv squared, and for m, let's use an integral here for this, and this will be the velocity of, not the ith term, but the qth term. And we have to square that. The relative velocity of VQ equals Vp plus Vq with respect to P. We of course derived this in the path by referencing a stationary position vector RQ and RP to a point O, and then we'll find RQ with respect to P, replacing VQ with respect to P with omega cross RQ with respect to P, where omega is some angular rotation here. We could then replace the above equation with components in this fashion, where VPX and VPY are the x and y components of VP, and x and y are the components of R. Grouping terms in I and J, we get the following. VPX minus omega y I plus VPY minus plus, that is, omega x j, where omega k cross xi equals omega x j, and omega k cross y j equals minus omega y I. Squaring this, we'll take the dot product of VQ dot VQ, and completing this square, we get VP squared minus 2VPX omega y plus 2VPY omega x plus omega squared R squared, where VP squared is the magnitude of the vector VP, and R squared is the value of x squared plus y squared. Subbing back into our equation for kinetic energy, we get this, where these integrals respectively represent the total mass, y bar m, x bar m, and the moment of inertia of our body about p. Then our kinetic energy becomes 1/2 mvg squared plus 1/2 ig omega squared if p is our center of mass. Let's talk about now energy associated with forces. Suppose we have a rigid body with an applied force. The body moves along this line and finally ends up here. Then, this is our relationship for work of a force, and specifically in terms of the angle between our force and the path S, let's call this S, would reduce to this integral, which is a scalar. This integral essentially represents the area under our force versus S curve, where the force is in the direction of the path S between the points S1 and KS2. The work of weight can be represented by this relationship where minus W is multiplied by a delta Y, where delta Y is the vertical distance raised regardless of the path taken. This is if our datum is taken at the start position. If we start out higher and move to a lower elevation, then the work is positive instead of negative. The work of a spring with spring constant K is, the work is minus 1/2 Ks squared, where S is the distance along the path that the spring is stretched. Notice that this value is negative because the work is against the force, or rather the work is the result of a force against the direction of the motion. The work of a couple moment can be defined in terms of theta. We can think of this moment as due to some parallel forces r, distance r apart. If we define a midpoint between these two forces, then the angle here is theta. We can then find a differential element of work defined as such, where r over 2d theta is the distance moved along the differential arc length. This then reduces to fr d theta equals the moment d theta. The total work due to the moment then is the integral from theta 1 to theta 2 of the moment d theta. And again, this moment is just the area under the moment theta curve between theta 1 and theta 2. So to summarize everything, our kinetic energy is this relationship. When we look at energy associated with work, our work due to a force is this relationship. Our work due to a spring, this relationship, always negative. And our work due to a moment, this relationship, we skipped work due to weight. This relationship.